Okay, welcome to, this class on graphical models. So today we're going to get a lot deeper into graphical models. We'll touch upon dynamic programming, and what we're going to go through today is essentially directed graphical models, but a lot of the algorithms that we will develop will work just as well for undirected graphical models. And what undirected graphical models are will become a little bit more clear in the following few lectures, but basically think of those as structured probability distributions where you don't have a clear causality path. Okay, so one thing that is quite important is you should all attend, the recitations anyway, but this time it's really important because otherwise you might have a little bit of trouble solving one of the assignments. Because what we're going to do in the recitation is cover structure inference. So basically we'll cover the Chow-Liu algorithm for directed graphical models for essentially figuring out what the structure of the graph is that we'll be doing inference over. So what that means is if you don't attend the recitation, or at least watch the video, you will find it rather difficult to follow or solve the assignments. Okay. The next time the assignments are going to be only 3. They will be a little bit longer than the 4 usual ones. So overall workload should be the same, and one of them will be structure inference. Okay. Are there any questions from last week? Okay. No questions? Okay. If you have any questions, also, just grab me right after class, that's fine, or come tomorrow in the office hours. So just to recap from what we did last week. So we started looking at directed graphical models, and here I had a very, very simple assumption of causality, right? My assumption of causality was that, basically you make it through college if you're either smart or if you are strong, or you make it through college even if you don't have any of those qualities just by accident, right? So the 10% of people who don't have any of those qualities make it through college, 80% who are either smart or strong make it, and 90% of those who have both qualities make it. So in other words, the observation of, graduated from college is a random variable that's causally influenced by, in this case, B and S, brain and sports. Okay, so now you would clearly think that, brain and sports are not really dependent on each other. As a matter of fact, we don't really model them accordingly. So now you can actually start asking questions, what happens if I were to do things like, observe that he graduated from college? Are the variables still independent? Well, most likely they aren't. Because if I know that you graduated from college, and I know that you are very sporty, maybe you didn't have to be smart to make it through it, right? Or vice versa. So basically what may happen is that those random variables now actually might be anti-correlated. And we're going to see something like that, and this is what we went through last time. I just want to recap, because it's a fairly subtle point, and people get that wrong all the time. So there's dependence, but there's no causal dependence in this case. Because, graduating from college doesn't make you any stronger or smarter. Okay. So if I were to look at just, the co-occurrence between those random variables, S and B, then, since they're independent, I get this table over here on the left-hand side. So that table should not pose any challenges to anyone here because, I assume that, P of brain is 0.1 and P of sports is 0.2, so the chance of both occurring are 2%, right? So I just, take that vector, take the outer product of the vector with itself, so this is how you would do it in MATLAB, and there you have it. Okay. Now, the other matrix that I have is the graduation matrix, right? So this matrix, it's just any matrix with entries between 0 and 1. They don't have to sum up to 1 in each direction, but we know that they're bounded from below by 0 and bounded from above by 1, right? Because they're probabilities. So now if I want to get the joint distribution over all three events, right? So P of graduating, sports, and brains, right? Then that's what I need to write out, because I know that graduating is conditioned on sports and brains is given by the right block. And I know that these two things are given by, well, I mean, the product of those two is this matrix over. Any questions so far? So I element-wise multiply. So I get this matrix here. So, you know, these are just the chances that among, you know, the population I find somebody who has those attributes. You know, it's a 1.8% chance that I find somebody who graduated from college and is strong and smart. And there's a 7.2% chance that I find somebody who graduated from college who is neither of that, right? So that's all fine. Now if I want to condition on graduating, so if I want to condition on G, then, well, what I need to do is I need to take all those numbers and divide them by the sum of it, right? That's just Bayes' rule. So if you think about it, we have P of S and B conditioned on G times P of G is P of S, B, and G. Right? That's Bayes' rule. So from that it follows, well, the thing is we need to compute P of G. So P of G is nothing else but the sum over S and B of P of S, B, and G. Right? So therefore, it follows that P of S, B given G is P of S, B, G divided by the sum over S prime and B prime. Actually, let me just make it primes here right away. Doesn't really change anything. P of S prime, B prime, and G. Right? Bayes' rule. Now, that sum in the denominator is exactly the sum over those blocks here. So I divide pointwise, and I get this. So now I have the conditional probability of being smart or brawny given that you graduated from college. These numbers now have to sum up to 1. And then I can do interesting things with it, like I can ask, you know, what are the chances that you're smart if you graduated? And well, they are quite obviously higher than the chances of just any random person, you know, being smart. So that was initially 10%, and it goes up to 27.5%. And likewise, I mean, chances that you're sporty if you graduated are now 54% rather than 20%. Right? And those are the numbers that I get by summing over the row or the column respectively, right? Because for sports, right, I need to sum over the lower row of that matrix. And for brains, I need to sum over the right column of the matrix. Okay, so that's all fine. Now I can ask further questions, such as, you know, I condition on 2 variables rather than just 1. So I could condition on graduate and sports, and I want to ask, you know, what is P brain? And so what do I have to do? I have to look at the row, you know, at the lower row, right? That's basically P of sports and brain, so I just apply that same reasoning again. Right? So what we have is that P of brain given sports and graduation is just P of prime and sports given graduation divided by the sum over, well, B prime P of B prime S given G. So, same equation as up here, just that now we only have one variable left. Okay. And if I do this, well, I get, 11%. So this is basically back to, the, average. And on the other hand, if I know that, well, you're not sporty, then chances are even higher, right? Then, you infer that, chances that you must be smart if you aren't sporty are 47%. So now all of a sudden those variables are dependent on each other, except that, well, this only happened by observing an additional variable that is a result of, well, S and P. So this is sometimes called explaining away. So if somebody tells you about explaining away, that's the phenomenon that we're looking at. So here's the math again. Now, here's another thing that could happen. Maybe going to college makes you smarter, and maybe it makes you sportier. So in this case, well, S and B are actually dependent on each other. Because, well, there's a causal connection now. If I send you to college, you're going to become stronger and smarter. Because you study and because you probably go to the gym. Now, however, if I tell you whether you went to college, all of a sudden those variables become independent of each other. So this is rather counterintuitive. So in one case, by observing something, things become dependent. In the other case, by observing something, they become independent. It all has to do with the direction of those pesky red arrows, right? In this case, well, things became dependent by observing, and in this case, they became independent by observing. Is that sort of kind of clear to everybody here? Okay. Any questions? Because this is a fairly subtle point, and if you understand that well, you'll be able to do homework 1 really well, which will be a graphical model about your chances of actually doing your homework. Okay, slightly self-referential, but anyway. So, I mean, just to show that this works in other cases too, let's say I have a website and I have a server and I have a database, and then, likewise, they become independent. So in practice, what happens is, let's say I know that my website is working or it's broken. If it's working, then I know that both the web server and the database have to be working. And if it's broken, then I know at least one of those two components have to be broken. And furthermore, it tells you also then, if it's broken, well, if I know that the web server is broken, then probably after I fix that, I will say, well, most likely I've figured out the problem. Now, usually life isn't quite that easy. So you might actually have that variable W not being observed directly. Let's say, this is a very simple model of how a major internet company works. They have a database backend, they have a server, then they display a web page, and the user does something. And in many cases, the first thing that you're going to notice is, if something is wrong, is that the users don't end up doing the things anymore that they're supposed to do, namely click on ads and therefore make you money, right? So basically, if all of a sudden your ad revenue drops, you can infer that maybe something is actually going wrong on your site. Well, you probably want to have other ways to monitor that rather than waiting until the money stops flowing, but this would be a very effective way of telling that something's broken. So in this case, even if you don't observe the website directly, you can still infer from the user action, which may not be a deterministic random variable, that maybe the site is broken, which then will make you, check all those various components. And, well, why would you do that? Because you would actually need a lot fewer parameters. And so this is really useful if you have a nice causal direction. So this is how you would probably want to design your system anyway. So you probably wouldn't want to engineer something where the web server has to be up and running for the database to work, and the database has to be up and running for the web server to work. So if you build something, you do not want to have cyclical dependencies of that form, because it just makes it really, really hard to recover from a crash. You've probably run into this problem at some point when you installed Ubuntu packages or so, at least if the package manager is broken and you need an upgrade, then you have two packages, both need to be upgraded, and you can't upgrade one because the other one hasn't been upgraded the other way around. At least on Mac ports this happens all the time. It's exactly the same case where you don't want to have that kind of cyclical causal dependence. So that may sound abstract. Let's solve an age-old problem with that. Well, who came first, the chicken or the egg, right? Okay, well, besides the fact that this is a rooster and it doesn't actually lay an egg. Okay, so let's assume the biologically implausible that the rooster lays an egg, right? But then from the egg hatches a rooster. So what happened here? It's clearly wrong, right? Besides the biology, obviously, but so I could go and model P of chicken given egg times P of egg given chicken, but that doesn't give me a proper probability distribution. Okay, all awake? Okay. So, well, what is okay to do is if you have something like P of chicken given egg times P of egg, or P of egg given chicken times P of chicken. Okay. So question, how could you fix that model? What is wrong with that model here? Okay. What's wrong? Does the chicken lay its own egg? No, exactly. So what you actually have is, you have that type of a process. So we have chicken I, which lays egg I plus 1, which then, from which hatches chicken I plus 1, from which then lays egg I plus 1, A plus 2, and so on. So in other words, what we really completely swept under the rug here is that we actually have a time series. And now all of a sudden the causal dependence makes perfect sense, except that, yeah, okay, I screwed up the biology here. Okay, well, you need the rooster too, but fine. So what happens is that if you want to have those causal dependencies, you actually need to make sure you're establishing causality between the right random variables. Okay? So remember that picture and resist the temptation if you at some point want to do graphical modeling. And I can tell you I've seen that more than once, that people came to me and said, well, hey, I have this model and hey, it works because our click-through rate went up in some unnamed company, and no, it wasn't Google. And I told them, but look, your graphical model is broken. And they kept on arguing with me that it must be right because it works. Well, it may do something marginally useful, but it's statistically wrong, so don't do it. Model things in the right way. Okay. So, any other questions about chickens, eggs, and philosophy? Okay, good. So here's the general structure. So we take some directed acyclic graph. And the important thing is the acyclic part. Because, well, maybe you don't have the chicken and the egg, but the chicken and then the grain and then the egg or whatever in some causal loop. And now, you don't want to have loops in it, because otherwise you get exactly those cases. And I'll show you afterwards a way how to deal with cases where you actually have a loop structure. Because you can still model things. You can model correlations in this case, but not causality. Okay. But here for a directed graphical model, what we have is we have some graph of what depends on what. And then all you do is you just write out the joint probability distribution by saying, well, the child depends on its parents. And that's exactly what I did below here. So if you go through, well, vertex 1 doesn't depend on anything else. So you just have P of x1. Vertex 2, well, depends on 1. So you have P of x2 given x1. Vertex 3, well, depends on x2. Okay, so that's fine. x4, well, that depends actually on 3 and 7. And you just go through. So this is very straightforward to compile a directed graph into a directed graphical model. Any questions here? Yep.
Could you please go to the last slide, the chicken and egg?
The chicken and egg? Okay.
Suppose that this is two states and it forms the Markov chain. So we can use a cyclic graph to model the chain states.
Ah.
Is there any difference between them?
Ah, okay. Very good question. So this is something that people sometimes get confused about. So you might have seen a state transition graph, right? So you have states 1, 2, maybe 3. And maybe from 1 you can go back into 1 or you transition into 2. From 2 you transition into 3. And from 3 maybe you transition into 1. Right? Now what this guy here does is it models which variables may follow each other. So you could have, for instance, in this case I can write it as follows. So P of, well, 2 given 1, and let's say you have a probability of 0.1 here, so this is 0.9, this is 1, this is 1.
Could you lower the brightness on the table? It's not really showing up. There should be a button on the table that can notice the brightness.
No. But if you want to find a button for me, I'm more than happy if you come over. But the thing is basically my hands are too dark. So as soon as I remove my hands, it works out, right? Because it automatically calibrates. Okay, so what basically happens is, I'll try not showing my hands very much. Maybe that helps. So what you would get is P of 2 given 1 would be in this case 0.9. P of 1 given 1 would be 0.1. And P of, well in this case, 3 given 1 would be 0. So what you could actually do is you could write that entire state transition matrix where we have states 1, 2, 3, 1, 2, 3, where we have the probability 0.1, 0.9, and 0. Now from state 2 I can only go into state 3, so we have 1 here, and 0 and 0. And from state 3 I will only go into state 1. So this is basically P of Si plus 1 given Si. And this is a really good thing if we have such a matrix, if we have such a graph. Because it means that a lot of the entries in this matrix here are zeros. In other words, our transition matrix is going to be sparse. That is something that can happen in addition to having a directed graphical model. The directed graphical model in this case would be just a simple chain. As a matter of fact, that will be a Markov chain. And each of those variables here can take on one of those 3 values. And if it does, then, well, the next one will be of a certain time. Whenever you have stuff like this, dynamic programming, and I haven't explained to you what dynamic programming is, but once you'll see it, you'll see that it then becomes easier. Okay. Awesome question. Thanks. Any other questions about that? Okay. So now, once we have such a joint probability distribution, life's good, right? Because if we observe everything, then, and if we know the structure beforehand, then, you know, we take the log of this, and the log of products, well, becomes, you know, the sum over the logs. So I basically now, all I have to do is just model each variable individually, given, you know, its parents. And that's more or less the best thing I can do, and I'm happy, right? So the problem is solved. And if you always observe everything, we can stop here. The problem is that in most cases you don't observe everything, because some variables may actually be unknown modeling variables, or because you, well, observe only parts of the data. So, for instance, if you take your cell phone, right? You probably have a 5 megapixel or 8 megapixel sensor in your cell phone. And depending on how expensive your cell phone was and how good the tolerances of the manufacturer are, there might be dead pixels in the cell phone sensor in the camera. Okay. Maybe not if you get a super fancy phone, but if it's a slightly more affordable one, you might have a couple of dead pixels. Now, do you see those dead pixels in your camera when you take a photo? No, you don't. The reason why you don't see it is because you actually, there's an algorithm inside the camera which interpolates the value of that dead pixel given all of its surroundings. And this way, you can actually get away with a couple of dead pixels without anybody ever noticing. Okay. And this is exactly one of those cases where you performed a very, very, very primitive, in some cases, graphical model to just infer the value of those dead pixels. Now, you've probably seen similar things if you had noisy images. So you take a picture with, you know, very high ISO. Maybe you take a picture at a party at night and it's really dark. Then afterwards you load it up in Photoshop or Lightroom or iPhoto or whatever, and you press the button denoise. Well, what it does is it basically solves the problem for a graphical model where you say, well, you know, there was the underlying picture, there was what I observed, and I'm trying to infer, based on what was underlying and what I observed, what the underlying random variables would have been. This is again a case where then afterwards I don't observe everything. And this is exactly where all the really fun algorithms for graphical models come from. As a matter of fact, for image denoising, one of the key issues is not just that it's accurate, but also that it's fast enough. Because, you know, your cell phone doesn't have much processing power, your laptop doesn't have much processing power relative to what you'd want, and so you need to have algorithms that are both reasonably accurate and sufficiently fast to implement. Okay. But that'll all come in due course. Okay. So here's what we have. We have the directed graphical model, just random variables depending on their parents, and well, if you observe something, then it actually can make things dependent. So let's look at that a little bit more formally. So we're going to go and discuss an algorithm called the baseball algorithm. Base as in Reverend Base. So the first part that we've already seen, well, no, we haven't seen that part yet, the chain, is suppose I have a, well, we have seen the chain before, but let's say I have a joint distribution P of A, B, and C is P of A times P of B given A times P of C given B. Now if I observe B, then, well, we can just work out what it is, right? Bayes' rule, well, it's this fraction here. And then I can actually go and pull out the terms dependent on A prime, and the terms dependent on C prime in the denominator. Now once I have this, since I'm not summing over B, I basically get something that factorizes into an expression only dependent on A, an expression only dependent on C. Right? And I mean, this is just algebra. And what that means is that now conditioned on B, A and C are independent of each other. That's this expression here. Okay. Is everybody happy with that expression? It basically means conditioned on the present, the past and the future are independent of each other. Now, some historians will tell you that this is not true. Well, it's not true if you don't have a complete characterization of the present. Because with present, I mean, well, the entire state of what the world is like right now, plus all the books and everything, right? And then it actually makes sense. The common cause part, well, we already looked at that, right? So we know that, you know, A and C are dependent if I integrate out over B. It's the middle equation. It's just a recap from what we saw before. That was basically, you know, college makes you smart and strong. But if I condition on college, then of course, brains and strength become independent. And this was the one that we spent actually a lot of time on, namely where conditioning on the joint outcome, things become dependent, whereas otherwise they were not. Okay, so this gets us to something called d-separation. So if I have a general directed acyclic graph, I might want to ask a question like, well, given sets of variables A and B, are they independent of each other, conditioned on C? And there's a very simple algorithm, it's called the baseball algorithm, which says that, well, all I have to do is just perform a reachability calculation. So you start with a vertex in A, and you try reaching a vertex in B, and you basically condition on the vertices in C. And if you cannot reach it, then for none of those, no pairs between A and B, then, well, we have conditional independence. Okay. So here's the example. What people often do is they mark observed and unobserved random variables slightly differently. So observed is typically shaded in black. Sometimes I'll be just shading it in a different color, just because things are more readable. And so these are slides. This is a picture taken from the late Sam Roweiss's slides from 2005. And here are those three cases again. So if I have a chain, so that's the top row, observing Y stops the dependence between X and Z. So I basically just, you know, follow that chain along, and if I hit Y, then okay, I stop. If, on the other hand, I don't observe Y, then the dependence goes through. That's what we had before for a chain. Then the common cause, that was the case where if I observe Y, if I observe the common cause, this is like, okay, I know that you went to college, so therefore, you know, whether you're smart and brainy, become independent, given that college makes you smart and brawny. Okay. Whereas if I don't observe Y, then the arrows go through. That's basically the middle graph over there. And then the bottom part was the explaining away, where observing the joint outcome makes the arrows go through, whereas not observing them makes the inference stop. You can easily see that because I can just go and integrate out this variable, and then those other two become independent. Now the last thing that you need is, if you just have, you know, leaves hanging off, it's essentially the same reasoning happening as before. Basically, if I observe, if I have a child and it's not observed, then, well, things don't go through. If I observe that child, then the information from the child, you know, comes back, and likewise the other way. Okay. So those edge rules are essentially, well, just additional spruce. Yep?
When you're calculating reachability, do you consider the direction of the arrow? Because in that case,
Very
how you bring those
And
Edges coming in.
yes, you can move against the direction of the arrow. So let's look at a specific example. Let's say we have, those variables x1 through x6. And I want to know whether x2 and x3 are independent of each other given x1 and x6. Note that this entire set of variables doesn't have to, cover all variables between 1 and 6. There can be some left out. Okay, so, well, let's start with, x4. Well, let's send the message towards x4, and it stops there. Because, it's an unobserved child, well, fine, nothing happens. Let's send a message in the direction of x1. Well, it's an observed parent, so again, nothing happens. If this parent were not observed, the edge would go through from x2 via x1 to x3. So now there's a third arrow that I need to follow, and that one goes through. It goes through because, well, x2 and x5 have x6 as a joint child. And observing the child makes x2 and x5 dependent on each other. Now, I know that this is a chain going from, x6, 5, and 3. So now, since it's an unobserved variable in a chain, I can just move up, and bingo, I get x3. So this is why things now are dependent. So I could make things conditionally independent of each other. For instance, if I were to observe x5 rather than x6. Yep.
So back to the color, this is like mostly because I don't know what's the meaning of this color.
Okay, so the colors of the arrows mean nothing, except that the red ones are the ones where I tried to reach x3 and I couldn't reach it. So basically, that's where the baseball algorithm terminates. Whereas the green arrow is the one that manages to reach x3 from x2. It's just a visual aid. Now, the black arrows are the arrows of the directed graphical model. So this is how random variables depend on each other. And all we are doing now is we are running this baseball algorithm to try and reach x3 from x2. So it's probably useful if you remember those rules, because this is exactly what you'll have to do for your homework on a graph that's a little bit bigger than that. Yep.
So I get it why this thing is happening, but by the reachability thing, shouldn't, when you're going from x2 to x6, shouldn't that get blocked basically because x6 is straight?
Okay, so x6 is observed, and so we know that x6 is a joint outcome between x2 and x5. That's basically the you graduate from college because you were either smart or brawny, right? And we know that observing the child makes the parents dependent on each other. So therefore, by observing x6, you actually create a dependence between x2 and x5, so therefore the arc goes through there. You then also manage to cross x5 because it's an unobserved variable in a chain. So everything propagates up. So you basically get you pass the hurdle at x6 because it's the common child. You pass the hurdle at x5 because it's an unobserved variable in a chain. And note how the arrow now goes against the direction that the green arrow goes against the direction of the black ones.
How it goes with the prayer starts to...
Sure.
Now this-
Sorry. Yep, there we go. So these are the rules. So basically, the left-hand side of that is really what we went through before, right? So let's just go through them, right? This was the chain. And we see that, well, by observing B, A and C are independent of each other, right? We knew that by observing B, A and C are independent of each other. And we saw that by observing B in this case, A and C become dependent of each other. Right? So now this is exactly what we have here on the left-hand side. So the chain is on top. Observing Y makes X and Z independent. Not observing Y makes them dependent. For the common cause, observing the common cause makes them independent. Not observing the common cause, of course, means that they're dependent. And then, well, here, observing the common outcome makes things dependent, whereas not observing the common outcome just means they're independent. So that's exactly the three transition rules that we had before. Are there questions? Yep.
So will this procedure work regardless of where you start?
Yes. So what you actually have to do, if you want to check for sets of random variables, you need to basically start from each of the random variables in A. And of course, if you pass another one in A, then you know that you've essentially taken care of that one as well as everything else. And then you keep on moving along this chain, and you try hitting as many variables in B as possible. So the way how you would implement it is, of course, not that you try for any pair until you've hit this path, but you basically, just, record whether you've already passed the vertex, and that's how you build it up. So this is how you would, of course, do reachability in time that is no more than number of edges in your graph. Sure, but you've probably all done graph algorithms at some point. Who's done graph algorithms? Awesome, most of you. So basically what you do is you store information about whether you've visited a vertex in the past, and then you use that for reachability. Okay. And then those last cases are simply if you implement it such that you can deal with edge cases. Because you want to worry about, if you have just, one vertex hanging off, well, do I need to take it into account? And so, for instance, if you look at the top right case, it's kind of actually pointless if you think about it, because, well, if you observe Y and, you would start from X and go somewhere else anyway, so, you can pretty much forget about those guys. Likewise here. Okay. So does that example now make a little bit more sense? So which variable would I have to observe for x2 and x3 to become conditionally independent? So suppose I let you observe two variables. Which one would I have to observe for x3 to be conditionally independent of x2? 1 and 5, exactly. Because then I've observed the child in the chain, so things terminate here. And 1, well, I've observed the parent, so this also terminates. So in this case, checking conditional independence would be easier if I started from 3, right? Because then, I would get blocked here, I'd get blocked up there, and I know it's game over. And you can also see that, of course, you could go and start from x3 and reach x2. If you keep on moving, you pass x5, that's fine. Then you can keep on moving because it's now the common child. So you pass x6 and you fit x2. Okay. So I can draw those arrows the other way around, the green one at least. I know that was slightly subtle, but yeah, okay. I mean, you basically just work it through. It's just very hard otherwise to get a good intuition by just looking at the graph. At least I would have trouble just by looking at the graph to tell immediately what depends on what. Okay. So said, we have dependent random variables. Observing things can make them dependent or independent. And then there's a very simple algorithm, maybe not the world's most efficient one, that lets you check things. And you only need to really remember those 3 rules in the bottom. Chains let information through, and then, yeah, if you have a common child or a common parent, things are exactly reversed. This is basics about directed graphical models. Yep?
Yeah, so now the best for, I think the runtime can, in the worst case, is exponential.
No, it would not be exponential. Here's why it wouldn't be exponential, because you would go and color each vertex. Right? So you start out from a vertex, you move to the next one, you then color it as, well, I visited that as incoming from a given vertex on my way to somewhere else. And so you can, through that, basically find out what's the reachable set from a particular vertex to all the other vertices. Okay, so that gives you the conditional dependent set for that vertex to everything else. Now, the other thing that you obviously through that know is that all those vertices on that chain, or on that connected graph that you now have, well, as you move along the directed graph that you get, they're all also depend on each other. Right. So, okay, what I mean by that is, if you have a vertex and you start off and you end up somewhere here, you know that for this vertex here, it also has dependence on these, and this vertex here also has dependence on these guys. So that makes your life a little bit easier. So you can reuse that information. So it would not be exponential. Whether you can do it in exactly quadratic time is a little bit more tricky to answer, but you can definitely, you could definitely do it in quadratic time in the number of, so basically number of vertices times number of edges. This would be a very primitive implementation. You may be able to do it in just order number of edges. As in proving that, well, okay, look it up, probably somebody has done that. Okay, that was a good question. So now let's look at some structures. So in most cases, people don't just draw, random, arbitrary, complicated, directed graphical models. Because that's actually really hard, because you have to sit down and think. So let's look at some very easy shorthands. And those things are incredibly common in a lot of applications. So basically, in most cases, you don't only have a single instance, but you have many instances of a kind. So for instance, here, it's one lecturer. Actually, it's 2 lecturers, so we have plate over lecturers. And then there are a lot of students in the class, right? And sure, all of you are, special and different. And, well, Barnabas and I are all special and different. But overall, we are the lecturers, you're the students. So therefore, modeling the relationship is one that I can very easily model by saying, okay, for I equals 1 to number of students, loop through, do whatever. For j equals 1 to 2, as in number of lecturers, do something in terms of inference there. So that gives you a much more structured way of dealing with relationships between random variables. And it also means that rather than writing plate notations and basically rather than writing out a graphical model and going crazy about it, you can compress it nicely in plate notation. So the simplest case is actually the following thing. I have random variables, x1, x2, x3, x4, and so on. They're all independent and drawn from the same distribution. And so just like you could write a for loop as in, print 1, print 2, print 3, and so on, rather than for I equals 1 to 10, print I, right? So just like you could do loop unrolling, you could write it out explicitly, but that is much more compactly represented by just saying, well, repeat the structure. So this rectangular box just means repeat the objects inside this box, and usually, and I was just lazy to write it out explicitly, you might also say which variable you might want to iterate over. In this case, we iterate over I. So it's just like in a for loop, you don't just say for, you say for I equals 1 to 10. Okay. Now, if we have IID observations, quite often they depend on, some parameter, let's say, mean and the covariance. And in that case, well, this is theta. So I can write P of x and theta as being P of theta times, the product over all the P of xi given theta. And the left-hand side is the standard directed graphical model that you will get. And then I can say, well, actually, I'm really sick of, drawing each of those circles separately. So I'm just going to draw a rectangular box over the xi's and say, well, repeat this. And they all better depend on some external variable theta. So that's the equivalent of a for loop. So this is a conceptually non-trivial innovation, and it lets you write out really large graphical models very efficiently. Do you have any questions about that part so far? I'll go through a lot of examples, but I just want to give you a bit of an idea of what's going on. Okay. So, now in supervised learning, we have x's and y's, and then the x's are drawn maybe from some distribution with theta, and then the y's, they are drawn given the x's and given some parameter vector w. So this would be a plate model. So now I have two variables in it. X and y's are both indexed by I. And then, they depend on W. And this is the joint probabilistic model. Can I leave something out in this context? If I always observe all the random variables X, can I leave something out here? Can I simplify this model a little bit? I mean, this is a bit different from what we always did in supervised learning, right? Okay, what was different?
Can you get rid of the data?
I can basically get rid of this guy here. And this essentially, so I basically don't need to model explicitly what the generative process for the x's is. At least in standard distributive learning, this is what you would do. However, as soon as you have missing variables, you very much care about modeling theta. On top of that, actually, if you think about it for, transduction, you actually do care about knowing the distribution over x's. Here's an example. Suppose I was now going to teach this class for 10 years. Then, knowing the exam questions for the past 9 years might give you some idea of what the exam questions for the 10th year are. I suppose you're already going to do that in terms of midterm versus final, right? So you're not going to infer that learning theory will never appear in exam questions. Okay. So this is basically how you can turn supervised learning into the simple plate notation. And as you would have expected, we basically don't really need the thetas. Actually, things are a little bit more complicated because you observe some of the y's and not some of the others. And yeah, that's yet another part. So here's something very simple, Markov chains. Does anybody have an idea of how to turn that chain into a plate notation? So have those xi's, right? And so what you actually do is, I mean, the plate notation isn't quite that formal. Or at least, I mean, you need to specify a couple of things. You could do this. And then it's sort of understood that here I have xi minus 1, and here I have xi plus 1. In some cases, people might also draw it this way. To indicate that, you know, this xi depends on these guys. So what is, so in other words, this plate notation, while it's very useful, doesn't always give you a very clear formal definition of things. So in many cases, once you need that, you're better off just, you know, reverting back to equations. But it's a very easy way of sketching what you mean in terms of dependencies between random variables. So you care about such stuff, for instance, when you sit down with an engineer and you try to come up with a good user model. So you could then, for instance, say something like, well, here's the user behavior, user I at time t. And you would assume that, well, what he does at time t will influence what he does at time t plus 1. Okay. And so we have that. What time? Then, well, whatever the user model is will influence his actions, A, I, T, J. So what you actually have is you have these guys here in it, and you basically get a smaller plate. So this means you're nesting for loops. And by the way, it just so happens that you have many users, so I do this. So here I loop over J, and here I loop over the user's I. And then you might say, well, they all depend on some parameter theta. Sorry. And so you can very quickly build up fairly non-trivial models of, for instance, you know, what ads a user might click on for an internet auction. And this is what you actually do in practice. The models that you get this way are often not insanely complex. You might have 1 or 2 dozen of those variables. You then need to specify how they really depend on each other, and then you run your inference algorithms. This gets you very far. Okay. So here we go. Here's a hidden Markov chain. So basically, this is what goes on in my mind. This is what comes out of my mouth. So these are observed. This is what I'm thinking of. One would hope that what I talk about is correlated to what I'm thinking of. And, well, this is what you get. So now I have an observed random variable, the blue one, conditioned on a hidden one. And the observed one doesn't depend on anything but the hidden one, but it's the hidden one that strings everything together. This is more or less how speech recognition is done. I mean, the models are a little bit more complicated, but that's more or less what happens. And then you can also go and compile those plates into equations. There you go. So you would probably argue, at least I would argue, that this is much more intuitive than what's on the left-hand side. They're equivalent. Yep.
So how do you distinguish the parallel and each?
As in terms of implementation?
No, I'm just using description for you use the box to describe the chain. Right?
Okay, so Okay. Oh, so you mean something like this? Okay, let's write it out. Let's pick something very simple. So we have essentially, this is basically a nested for loop. So let's do something like topic models. So taking digital allocation. So we have a topic distribution per document. Then, and that happens, for each document you get its own. This then influences a particular word, ZDI, so the topics for a word, and this then allows me to draw a word, WDI. And I have many words for a given document. And I have many, have many documents, right? And of course, those would depend on all sorts of additional random variables. I'm just omitting them. So this is called LDA. And I would have that P of W, Z, and theta would be the product D equals 1 to total number of documents P of theta D times the product over now D and I going to D and MD respectively, P of W DI given Z DI times P of Z DI given theta D. So this is the for loop. Okay. Does that clarify things a little bit? Or did you have another, or was it another question that you asked?
Yeah, actually, I asked about the parallel group. So like x1 point to x2 point to y,
Uh-huh.
x1 point to x3 point to y. So
I'm not sure I fully understand.
it's another chain of parallel.
So you have two chains. Is it that you have something of that form, and then you have another chain?
Oh, they all start at the same point and
Okay, but they run in parallel, right?
yeah.
Okay, so now the question is, if there is no dependence between these guys, then this is how you would write it as a plate. You'd get one guy as a plate, and you'd get the other guy as a plate. Now let's assume that they actually depend on each other. Then you will get this as a plate. Right? So the difference is that in this case, since these two chains are running in parallel and they don't know of each other, well, I might as well just write them separately. On the other hand, if they actually do depend on each other, then I need to put them jointly into one box to model this dependence explicitly, and then I just repeat that. Yep.
I think what was actually being asked was, so you have one node at the beginning, you have one node at the end.
Right.
And in the middle, it branches out into a bunch of nodes and then collapses back into.
Right. Okay.
And how is that different from the chain notation?
Okay. So yeah, that one's kind of hard to do. Yeah, that you can't really do easily with a chain. But I think I know what you mean. So where you would basically have some start state, and that then depends on some basically, let's call this chain A1, and this is called B chain, and then yeah, you basically write something like this. And everybody would understand what it means, but it's not really well defined. I mean, this is how I would diagram it. The math is, however, quite straightforward, because you'd basically just have, P of A1 given S times the product over I going from 1 to n minus 1, P of AI plus 1 given AI, times then the same thing on the B's, times P of the final state given AN and BN. That's what the equation would look like. But yeah, if I were to draw this in a paper, everybody will kind of understand what's meant. With better writing than my handwriting, obviously. Okay, let's move on. So one of the nice things that you could also have is what is called factor graphs. So where you would say, well, there's a couple of latent root causes of what I'm observing. Then I'm observing a whole bunch of things, and well, I actually would rather like to know what the root causes are. So for instance, the observed behaviors would be like whether somebody clicks on something, what the queries of a user are, which news he watches, which emails he sends, to whom he sends emails to, at what time of the day, all those things. The latent factors would be, what is actually a user's profile, what's the content of the news, what are the hot keywords, social connectivity graph, and so on. So what you're basically trying to do is you're trying to find a more compressed representation for what you're observing. So here's a simple case, principal component analysis. So independent component analysis would work similarly. So let's say X is a normal distribution for, I have some linear combination of those vectors, yi, vi. I'm drawing the yi's independently from each other, and I'm just adding some Gaussian noise to it. So if you were to do this and assume that the yi's are drawn from a Gaussian, then you would immediately see that, x's are also drawn from a Gaussian. Well, let's just quickly do this, right? Let's say that the yi's are drawn from a normal distribution with zero mean and unit variance. And I have some vectors vi, and I know that x is sum over vi, well, j, yij, because I'm drawing them independently for each of those guys, sum over I. And then I have some additional noise. So then what would be the mean of x? So first of all, what's the distribution of x in this case? So xj is drawn from what? From a normal distribution, exactly. It has zero mean. That's great. And it has, well, covariance matrix. So let's say these are drawn from a normal distribution of zero mean and variance sigma squared. So it gets sigma squared times the identity matrix, right? Plus, and then the covariance matrix here is V transpose. And that's more or less what you would do in PCA, except that you would set sigma squared to be 0, and you'd basically be trying to get those vectors V. Yes?
So VI is not a random variable here.
The VIs in this case are not random variables, but you could actually make them also random variables. And then you get an algorithm that's called Bayesian PCA, or in some cases also SPCA. So this is a Bayesian treatment for principal component analysis, and it is a bit more stable than just PCA. Now, if the y's yi's would not happen to be Gaussian, and that's not an unreasonable assumption, then this gives you independent component analysis. So let me show you an example of that. Who's heard of the cocktail party problem before? Okay. So those of you who haven't, you've probably been to a party, right? Did you ever go to a party with a really bad cold where one of your ears was clogged? Okay. Okay. You're not really party animals, right? So you stayed at home and slept. But you've probably taken a plane, and at some point when you had a cold and then one ear didn't work, and you get off the plane, and it's just really hard to understand anything that's going on around you. You can also try the following thing: listen to me and close one of your ears. Try that now, then try understanding what I'm saying, and you'll find it really hard. At least, more or less, because, I mean, probably harder than otherwise, because what happens is that your head, because you have two ears, so it actually does all sorts of nice signal processing in your head while you're trying to listen to me. So the signal processing that it does is it cancels out echoes, and it also cancels out that other pesky guy to your left who keeps on talking, right? Because at least you're trying to listen to me as opposed to that guy. Maybe the other way around, but basically you probably know when you go to a party, you sometimes can try to listen to a specific conversation or to another one, and so you're basically tuning essentially, your auditory model towards a specific conversation. So what you're doing is you're basically performing demixing, as in nonlinear demixing of the auditory signals, which is what comes here in from the microphones, and then you're trying to figure out again what the underlying sources are. And this works really well if the two conversations are very different. Let's say, somebody has a very low booming voice and somebody has a very high-pitched voice, then it's really easy. And it's really hard if they say the same thing, which is why if you go to a concert and there's a choir and they all sing very much in harmony, it ought to be really hard to hear out an individual singer. As a matter of fact, if you can hear out a particular singer, then that singer is not doing a very good job, right? So this is exactly one of those cases where, you have perfect dependence between the signals, so it becomes really hard to demix. Whereas if the signals are nicely independent, it becomes very easy. And the idea of independent component analysis is to find exactly those independent signals, which is what we had here. Right? So those circles on top are the independent signals. The blue guys are what we observe. If there were a bit more time in this course, we could go into this in a lot more detail, but I just want to at least give you an idea of what independent component analysis is actually all about. And the cocktail party problem and the linear demixing is sort of the simplest thing you can do. Any questions so far? Okay. Here's another structure. You've probably rented a movie on Netflix or on Amazon or Hulu or whatever. And so what you have there is, and this is why I want to walk you through this, you have users and you have movies. And then you have ratings. I could model the users very nicely, through, let's just take a new page. Here's a simple model for the users. I have some parameter alpha, which is a common cause, and then I have users, UI. And I get a lot of those. Each new user who comes along, well, I just, generate his profile. I could do the same thing for the movies. But of course, that's not very useful because I actually want to sell movies, right, to particular users. So I have those ratings, Rij, which tell me whether a particular user rated a particular movie. And now it so happens that basically those two loops actually intersect. So this is what would make any C code really fall over, because you have nested for loops which don't really look at all the entries, right? And this is also what makes implementation of collaborative filtering algorithms sometimes a bit more interesting, because you don't iterate over all possible user-movie combinations. So probably there's going to be a fair distinction between people who've watched Notting Hill and those who watched maybe Die Hard 2, right? And so in other words, you actually don't really rate all the movies. The fact is, you can actually use this information to improve your recommendation model, but that's beyond this very simple structure. So the fact that you didn't rate Notting Hill and that you didn't watch it tells me already something about how much you might like such a movie. So what you really have is you have users and movies, then the ratings being only a subset. And yeah, you can do that a lot. So the statistical model that arises from it would be, of course, product over I, P of ui given alpha, product over j, P of vj given beta, times product over I and j pairs in some set of ratings, P of rij given ui and vj. And you could make this more interesting by, for instance, having a temporal dependence and adding a lot of other parts to it. And yes, you can use that for movie recommendation, but also for things like recommending answers, recommending friends. You could even use it, my guess is probably OkCupid is using something like this. And the other thing is, of course, rather than just latent variables, you could also observe some things and then use both things. So the key issue is now, well, how do you design this? How do you make it computationally tractable? And look at the dependence and then do all the inference. And this concludes it for today. We'll do dynamic programming on Wednesday. So basically, think of chains and similar constructs as mechanisms for very quickly sketching out graphical models. So more than anything else, I hope that at least you remember some of the common structures, such that when you ever have to solve a problem in practice, you can just go and use these constructions as inspiration. And then you need to look up exactly how it's done. Would you mind stopping the camera? Any questions?